So I had the great privilege and honor of sitting in on some of the talks yesterday. This is a fascinating topic. We're sort of out of order because I'm here more today than yesterday, so we get this overview today. This is a very large topic. It includes, of course, star formation, and at part of this I will take you on a sequence zeroing in on some regions of star formation, and then to continue that sequence you would go back to some talks from yesterday. But I want to give you sort of a big picture of how star formation, starting with the big picture. This is a simulation of the Big Bang. And of course, there are the filamentary striations and clusters of galaxies form at the intersections, typically between 2 or 3 or some number of filaments. And the physics behind this is something you actually know from everyday life. If you imagine some expanding glob of goo that wants to attract and yet is exploding at the same time, it will have structure like this. So I pulled out a movie of an exploding drop of water. And look carefully. It makes filaments, it makes globs. And there's actually a Hubble law in here, because the things that are in the center toward the end we're moving slower, because it all starts at the same time. So it's simply a combination of an overall expansion. In the case of cosmology, it's the coordinates, satisfying Einstein's field equations, in addition to an attraction, which in this case is surface tension, but in galaxies it's gravity. So here's the star formation rate in the universe. This is plotted on a linear scale with time, which gives you a good perspective if you're thinking of the origin of life, because that's squeezed way over on the left. Star formation rate ramps up very, very quickly from the Big Bang. And this rise here is because the virialized horizons of various units around forming galaxies is growing. Initially, it's all expanding, but with the Hubble flow, the atoms that are close to each other are hardly moving apart, so they turn around and become gravitating first. So you have tiny little gravitating horizons or virial horizons at first. But then as time goes on, more and more, as the masses get bigger for these condensations, more and more falls back in. And today, that's still happening. What's falling in are clusters into clusters, or galaxies into clusters. And that will continue to happen. Okay? Stars are forming inside these virialized little pieces, typically in disks. So you can think of this ramp up as the growth of galaxy disks, with stars forming in them more and more because the total area of these disks is growing up. At the same time, the universe is getting less dense, so that gravitational timescales are going up. Gravitational timescale is inverse square root of density. That's happening all throughout this. So things are slowing down. The collapse is slowing down more and more, even from the beginning. But at the beginning, the virialized horizons are growing faster than the slowdown from the lower density. Eventually, at around a billion years into the universe, eventually the lower and lower density from the expansion starts to win, and then the accretion rate onto these virialized halos starts to go down. And that's why the star formation rate decays. Now, if you're thinking of the origin of the Earth, we're pretty late. Our Milky Way formed at a much brighter time in the universe. When the Earth formed, our Milky Way had already died down by a factor of 5 or so, and when life formed, the galaxies, the local group, the whole universe had quieted down another factor of 4 or so from the time when the Earth formed. So if you're wondering what the environment of the Sun was like when the Sun formed, it was more active than it is today by a factor of 5 or so. More supernova, more star formation everywhere in the universe because accretion rates were faster, even onto the Milky Way. If you're thinking about what the universe was like even earlier in the Milky Way, we're not even at the peak. We're sort of a bit downstream from the peak. What did the universe look like then? This is the ultra-deep field. And now I'm glad the lights are a little low. This includes the UV. If I zero in on a place like this and blow that up, you can see galaxies at that time were very different looking. They're all very irregular. They're clumpy. Whereas galaxies today are extraordinarily smooth. So this is really a big change in morphology. Virtually everything then was extremely clumpy and irregular, and virtually everything now is very smooth. Sometimes there are stellar structures, which are also smooth, like bars and spirals. So here's that cosmic star formation rate, now plotted log 1 plus z. And it's a nice symmetric curve. Redshift 2 is about the middle, and you already heard that at the rising part, that's because the virialized horizons are increasing. But look at how everything differs in those days. Lots of turbulence, because you have very fast accretion onto deep potential wells. Intense star formation feedback. Star formation rates are fairly high, and the galaxies are still small. High gas fraction, maybe 50%, 80% at those early times. Gravitational instabilities are wild in the disk, making these big clumps. Because of the high turbulent rate, the Jeans length is very large compared to the galaxy size. That ratio just depends on the velocity dispersion divided by the rotation curve, which was high then. You have thick disks for the same reason. The Jeans length and the thick disks are about the same size. Big compared to the galaxy size. So all of today's thick disks, most galaxies today, Milky Way included, have a thick old part of the disk and then the thin part where stars are forming. That thick part, that was the disk that formed at z equals 2, 3, 4, because the galaxies were much more turbulent. Because of all these big clumps, there are larger disk torques, which would not drive spiral arms. It was too irregular, but would still have torques and cause mass migrations, radial migrations. At that time also, lots of accretion to the center, so you have quasars. On the other side, things have quieted down. Low accretion rates, relatively low star formation feedback, marginal gravitational equilibrium. Stellar gravity typically exceeds gaseous gravity. So today we have spiral arms, not big gassy star formation clumps. And bars, rather weak torques. You have random one-by-one stellar scattering rather than whole torque things from big clumps. You get the red and dead galaxies, which have already exhausted their gas or stopped their accretion. And over time, continuing this buildup, you get the massive galaxy clusters. Okay, so that's a cosmology in a nutshell. I'll take a minute or so if there are any quick questions about this before I zero in on a local region of star formation. Yes?
So what was the scale height of the disk and how it changed within the time?
Yes, so that can be directly measured in deep fields. We've done that now in a couple papers, and it's a kiloparsec or so, 800 parsecs.
It didn't change this.
And today it's only 200 parsecs.
Okay.
Yeah.
Yeah, so the sun would have migrated probably a lot from where it was born to where it is now.
This is a very good question. So no one knows in particular where particular stars were born. We do know from the dispersion of metallicities that there was some spread because the local stars have a spread in metallicity, which is probably a spread in their birth sites. We sort of fit into local metallicities, not quite. What drives some of this migration is just spiral arms, and the spiral arm history of our galaxy is not known, whereas simulations, you know it, so you know there's all this scattering. So we could very well have formed at a different place. We could not have formed in a thick disk and settled to where we are now. That goes the other direction. And clouds would scatter as well. Certainly, we do know that when galaxies grow, the radial scale length of the exponential disk increases with time because accretion tends to be in the outer part, so it makes it bigger and more spread. And so when we formed a half a Milky Way ago or a third a Milky Way ago, our Milky Way was probably smaller. So either we were closer to the edge then, or we formed in also and moved out with it. So we don't really know. Yes. Yes.
So which came actually first, stars or galaxies?
Well, the dark matter, it drives everything. That's the dominant mass over baryons. So that comes first, and the baryons fall in second. And then the baryons will make stars for the first generation stars, probably in very small, like dwarf galaxies are even smaller today. We don't see directly the remnants of those first generation stars right now, like black holes or something. They're there probably. We don't know. We see the early elemental abundance from those first generation stars. So those stars form first. And if you call the thing around those first stars galaxies, you can do that. They're probably low mass. The next thing are the globular cluster systems and so on. And then everything builds up from there. So stars form before galaxies, but stars form in galaxies if you define a galaxy as the dense part where stars are forming.
Yeah, I had this question which often comes up when people study things, systems like the Magellanic Clouds,
Yeah.
which are metal poor.
Yeah.
And then they say, this is great because that tells us cosmology, I mean, metallicity is low, but the dynamical structure is very different of a Magellanic Cloud as a dwarf galaxy,
Yeah.
which you just pointed to, that they exist in great numbers early on.
Yeah.
So what is the difference
Yeah.
between the small Magellanic Clouds, metallicity a fifth, and some way look back?
Yeah, okay. So now the observational answer is pretty clear. You probably know that bigger galaxies are more metal rich. That's the mass metallicity relation. That is mapped back at redshift too. And that is also true for all redshifts where it's observed. So today we have a mass metallicity relation that's fairly high, lots of metals for the mass. But back in time, that tends to decrease, always showing a mass metallicity relation. So even at z equals 4, there's a mass metallicity correlation, but a lower metallicity. So the youngest, at the beginning, when the Milky Way was small, it would have had a small metallicity then, because there was a mass metallicity relation even then. The bigger galaxies then are the giant ellipticals today. Okay? So now, the current thinking is that this mass metallicity relation is not an age relation. It's not because low metallicity things just haven't churned many star generations yet. It's because they are low mass galaxies and they weakly hold on to their gas. So supernovae blow away the metals. That's the idea. More massive galaxies hold on to their gas, and so the processed material can't get blown away. It stays inside the galaxy. That's why they're more metal rich. And that would be true for all times, because it's just a dynamical effect with the potential well. Those extra metals stay around the halo. They're eventually recreated, so eventually all of the metallicity goes up, because there's some cycling on the big accretion time scale. But locally, at any one time, it could be just a feedback effect. Okay, so let's zero in. Here's the Milky Way. I think you can see this. Here's the large and small Magellanic Clouds. Here's Orion. Gum Nebula, there's Ophiuchus. Over here's Taurus. This is Andromeda. That's the Hyades cluster, the California Nebula. The whole picture. You can see Gould's Belt, if you like, because Ophiuchus is high, and Orion and Taurus are low. Let's look at Taurus. This is the same orientation. That's the Pleiades, the Hyades. Those two little dark clouds, if you see, do I have a pointer up here or a stick or something? I have sticks. I remember seeing sticks. Here. Sticks. Or is this for discipline? Look at here's a little star, see that? Now look at this filament right below the star. Okay, so I'm going to zero in on that. There it is. It's a different orientation now. And it's a dark cloud. Barnard, who made the Barnard Atlas in the early 1900s, saw these very well because his photographic depth was just right to not see through these dark clouds, so they all look dark against a background. But now we can see them in the infrared. This is at 0.8 microns, and they glow because it's cool dust. You can see all the structure. There are little knots where stars are forming. There are little loops here. Generally, it's a filament. And it's a lumpy filament, like the snake that just ate 3 little mice. If we look at the velocities, one side tends to be going away from us, the other side a little bit toward us. Here you see striations, which are a combing of the gas because of that flow, and the magnetic field lines are stretched out in the direction of this flow. So you get the impression just from this that there's a gas flow onto the filaments with a higher gravity in the filaments forming little lumps, which form stars. If we look in more detail, inside the filaments there are other filaments. And the stars individually are forming in these denser filaments in the regions with the highest mass per unit length, which is the strongest gravity. This is carbon monoxide. 1 to 0, showing the velocities. You can see velocity gradients. This is much more detailed than the one I just showed. Generally a gradient across it, some large deviations of velocity here, but you see all the little striations inside. Now I want to show you a movie. And I've put the shade down thinking this will be a little faint, so I hope we can see it. This is a magnetic turbulent box with gravity. And it's run already for 350,000 years, and what you're going to see is the time after that. So it's already set up lots of little filamentary networks with a filamentary ridge in the middle, and you're going to see star formation in that filamentary ridge. Look also carefully for little explosions here and there, because there's feedback. So here it is. Yeah, I guess you can see that. It's twisting around. It hasn't evolved yet. Here's the time. It hasn't started ticking the clock yet. Red is denser. You can see this dense spine in the middle. Now it's moving. Here's some star formation with little explosions. It's coming in gradually. Now all of these little wisps are partly sheets edge on, because you have turbulent motions that are shocking. These are all shock fronts. Or there could be real filaments where two sheets intersect. You had a shock and then another shock. So now you have a line. The stuff in the middle is a growing ridge. It's a filament. Because of gravity, it's pulling in all this other stuff. But there's star formation elsewhere too. You see in some of these cores, here and there, lots of it in this dense spine.
Very gentle.
Yes, this is a region of low mass star formation, Taurus. It is very gentle. You put a massive star in here, it'll just ionize it all and destroy all this. See, now you can see that filament. It's kind of in a sheet. The overall structure is a sheet, and then inside it has clefts, the filaments. Just looking at distribution of dust, for example, it looks filamentary everywhere, but you can't tell if it's a sheet edge on, or if it's crossed sheets to make a filament or some other gravitational filament. If you start with a sheet, it will condense into filaments and then blobs. Looking next door, that's that same filament that I just showed you in the infrared, but if we look next door, there's another little region, just like in the movie, HL tau, which I show you because it's so famous for the ALMA image of the disk. Here it is zooming in. Look at this little guy while we're at it. See this disk and the jet with little shock front knots in the jet? Here's another disk, HL tau. Herbig-Haro objects are emission line regions that are the result of shock fronts, which are the result of either bullets or jets or other high velocity debris coming off from the central star. Here's HL tau zoomed in with different velocities. You can see a kind of a conical shape here, and on the other side with a disk right in the middle, tiny disk. The disk is modeled here with the same orientation, and maybe you saw this yesterday. And of course, here's the ALMA image, which became so famous because that disk has structure in it, probably from planets moving around the dust. Okay, so that's another quick review of star formation, the low mass type. And I could take a minute for questions if you have any. Yes?
What is the typical temperature and magnetic strength in the center of this filament?
The temperature is still cold, 10 to 20 K. In the hot spots, it might get up to 20, 25 K, because this is low mass star formation. The magnetic field is still fairly low. It's in the 10 microgauss or something like that. It's not very much. This is a low pressure region. The average pressure is only factors of several above average ISM pressures.
And do we expect to see this magnetic field to be perpendicular to the elements always, or it depends?
Excellent question. It is in the case of Taurus. In the case where you could think of when gravity is dominating the field, it can comb it in. But you can imagine a shock front sweeping everything up, and then it tends to amplify the parallel component of the field in the shock front, and in that case it would be along it. In Ophiuchus, those streamers from the head, the field is aligned along the tail. Well, there are high temperature molecule transitions, CN, for example. There are also excited line emission, molecular hydrogen. Once it's fast enough. In Orion, of course, you see H2 molecular hydrogen emission. That's the vibrational lines. That can tell you 1,000 degrees. So shock signatures are often best seen as a chemical remnant, such as water. Water tends to be made at higher temperatures, and if there's a residual of water, you have the idea that there might have been high temperatures. The dust is often hard to see as a temperature elevation. The dust couples to the gas, typically at these densities. And the shock front, the hot part of the shock front is very, very thin. Then it cools. So you're kind of looking for a remnant of that, either as an excitation remnant or some chemical remnant of a chemistry that needed high temperatures, which cannot be explained any other way, like CN. HC is another. If you look at the distribution of rotational states of molecular hydrogen, which we can't do now, but Copernicus satellite did in the 70s because it looked at 1,000 angstrom absorption. You see a wide range of temperatures for the rotational states. So you know that a lot of that formed hot and it's just cooling down. So there are signatures that are subtle, and that's why very little is known actually mapping shock fronts right now. Atoms, molecules, cloud formation. So you know stars form in giant molecular clouds. How do molecular clouds form? Well, there are various theories, but it's all kind of muddled in thinking. Because some galaxies have very few molecules, and I'll show you, the LMC does. Others have lots of molecules, like M51. So it is not so much the molecule that's important as the structure and the gravity that determines star formation. And that's the point of this next sequence here. So here's the LMC, and here's a map of H1, that's the yellow. And the little CO is in the boxes. Tiny little dense parts of H1 clouds. And you see that some of it is around this big shell. Okay, so here the big shell of constellation 3 made this yellow H1 shell, and then the little knots around it are in this bright rim right here. It has a connector like a pillar. There's CO at the head and so on, here and there. 30 Doradus is here. Lots of dense gas here, perhaps because of ram pressure as this moves through the Milky Way halo. So if you're going to make a cloud here, it's not that you're going to coalesce together two different molecular clouds that are moving and just randomly hitting each other. It's a phase transition. Dynamical processes move all the gas. It may disrupt existing molecules because of bright UV light. And they would form again later in the denser regions. So molecular cloud formation is not coagulation of molecular clouds. It's a phase transition. It's just the gas you're moving, where molecules form or not, depending on shielding. A nice thing about having a galaxy that is mostly an observable phase, such as H1 or warm H1, which you can map. And here's a 24 micron. So this is the Spitzer map in 24 microns. The same thing was done for an H1 map. You can take a power spectrum. So a power spectrum means you take the sine and the cosine Fourier transforms. You square each, and that's the sum of the squares, and that's your power. Plot that versus spatial frequency. So big scales are here, 10 kpc. Small scales are here, down to a couple parsecs. And this is the log scale of the amount of Fourier transform power versus the spatial frequency on the log scale. So there are two power laws here. Kolmogorov turbulence gives a power law. And 3D Kolmogorov turbulence gives this slope. 2D gives this slope. So you're seeing here a transition from scales smaller than the thickness, where you have 3D turbulence, to scales larger than the thickness, on this side, where you have 2D turbulence. So where are the clouds? There's no characteristic scale. There's nothing big, nothing small. It's all a continuum. Okay? You can tell the thickness of this face-on galaxy just from the split in the Fourier transform power spectrum. And where does that split occur? Well, here's another way of looking at it. This is a Herschel map. That bend in the power spectrum occurs on this scale. So everything to the right of that bend, all that structure, is squeezed inside this scale. It's all the tiny, tiny stuff here. And everything on the left is bigger scale, everything you see with your eye. And that's the nice thing about taking a power spectrum. You really learn something different. Here your eye concentrates on all the big stuff. But all that big stuff is squeezed far on the left of a power spectrum, which tends to emphasize everything equally on a log-log scale. Here's the Milky Way. This is the H2 as seen by carbon monoxide distribution. In the Milky Way, it tends to peak at around 5 kiloparsec distance from the center. We live right around here. It's already coming down. Here it is the H1 distribution, which goes out much further. This is 35 kiloparsecs. 8 kiloparsecs is right here, so I've traced the H2 from over here onto these blue dots. You can see in the far inner parts, H2 is about equal to H1. But most everywhere else, H1 dominates. So this is like the LMC. Again, you have phase transitions, certainly near the sun, here, or further out, that are going to make any molecules that are there, or any star formation. You first are making molecules. Whereas in the inner part, it's equal in the two, so you can move molecules around. If you have some disruption of a molecular cloud from star formation, you're going to carry off chunks of that, and they're going to stay molecular, and they may reform or collect together later, because it's hard to totally dissociate them in the inner parts. Looking at the Milky Way from outside, of course it's hard to do, but you can map this. This was done, some of the first exercises of observing in H1, 1964. This is a map first observing the outer spiral arms in H1. This was from Australia. And this outer spiral arm here in H1 has a big lump here, and a lump, and a lump, and a lump. Again, it's a filament with that ate the mice. These lumps are 10 to the 7th solar masses, and this was known in the mid-60s. If we look now at CO, from modern observations, here's that arm, you can see it's lumpy also. It's not smooth. The molecules are concentrated inside big H1 clouds. So here shows this as viewed from the sun. This is negative velocity, so this is inside the solar circle in the 4th quadrant, so it's coming toward us, from 270 to 300 degrees. Here's a big H1 region, here's another big H1 region. All the molecules are concentrated in these big H1 regions. Eta Carina, a GMC, it's just a little tiny blob here, 10 to the 5th solar mass, inside a big blob, 10 to the 7th of atomic. So there's a hierarchical structure. The molecules hardly mean anything on this scale. Now this shows zero velocity, so we're at the solar circle, again 270 to 300. Here's a big H1 blob. Here's another one. Vela OB2 is over here. This is CO. This is H1. If we go further in distance now, so now we are at positive velocity, so we're outside the solar circle, again, still in the 4th quadrant, 270 to 300. H1 blobs, each of these are the McGee and Milton 10 to the 7th solar match H1 blobs. They all contain their cores of CO. NGC 3603, Hunts's favorite region. It's just this little guy right here, that's all. Not so special. And even further. Okay? So how do molecular clouds form in the Milky Way? Again, they're concentrations inside bigger things. Okay, so now let's look at molecular hydrogen versus CO. In the 1970s, the Copernicus satellite, which is the only satellite that's been put up to show, to actually map spectra at 1,000 angstrom, that's what you need to see molecular hydrogen absorption, mapped molecular hydrogen in the solar neighborhood by absorption lines through nearby OB stars. And so this was the first realization. There were earlier rocket programs by Carruthers, which actually discovered interstellar molecules. They had been predicted for a long time just by seeing dense dust concentrations that had very little H1. Bart Bach was saying this for a long time. So they knew there had to be gas there that was invisible in H1. Finally, it was seen in rocket flights, and then here in the mid-70s, seen systematically in most of the local diffuse clouds when the color excess exceeds about 0.1. So that's a visual extinction greater than 0.3. Hardly any visual extinction. Suddenly, the hydrogen turns molecular. And here's a spectrum from the Copernicus satellite. If you're a molecule of hydrogen sitting out there, you look around, the sky's dark. Because all your friend molecules are absorbing that UV light. And it's just black. And the story is when Spitzer first turned on, I was at Princeton at this time, so I was there when this was happening. When they turned on the telescope, they didn't see anything. They thought it was broken. And they were looking at the middle of a hydrogen absorption line. The sky was dark. And they said, you know, what's wrong? Out of focus? Is it, things not working? You know, you can't kick it when it's up there. So they just tuned the frequency and eventually it climbed up out of the absorption line. They saw the star. So hydrogen molecules, even in the solar neighborhood, do not feel terrible radiation fields which make them want to dissociate because all the other hydrogen molecules around them are absorbing that. And then they constantly reform on grains, and then they're constantly absorbing and photodissociating again. So the sky's kind of black for them. Let's look at a map again at Taurus. This is an extinction map. A sub K at K band, just from star counts. Here are the Taurus clouds, these are the filaments I showed you before. Well, let's see where the hydrogen molecules form in that map. This is a distribution function of column density or extinction. A characteristic log normal shape, so the average extinction is about 0.1 magnitude in K band, not much lower, not much higher. There's a little bit of a tail here, probably from gravity contracting the regions like the Taurus clouds where gravity is more important. And that threshold for H2 formation is right here, 0.3 magnitude, let's see, 0.033 magnitudes in K band. So where is that on this map? It's way down here. So virtually everything here is H2 rich. Whereas CO takes about a magnitude and a half, so CO transition is here. So where is that? That's mostly these darker regions. So this is CO, H2 everywhere, this is CO around here. And you can actually map the difference. Here's one of the regions. There's the CO boundary here, and the H2 boundary goes out further. So you got CO, you got molecular hydrogen, and then you got an atomic envelope. On the other extreme, you have M51, which is a higher surface density of gas, and it's almost all CO. Here's the H2 or CO fraction of the gas. The arm, interarm, you hardly see the interarm. Everywhere is H2, is CO. So here you can say, giant molecular clouds formed by coalescence of other giant molecular clouds, because everything is CO, everything's a molecular cloud. But that statement is nonsense. That's not, the statement you want to make for cloud formation, or the beginnings of star formation, is about structure. It's about things coming together, things getting denser. And all of these molecule parts are tracers of that. And that depends strongly on what the metallicity is, what the average density is. Okay, so GMCs are poor terminology, as you've just learned for many regions. ISM is a power law. This is also seen in the Milky Way. Everywhere you look at diffuse clouds, the power spectrum has the same slope, about 2.85 on a 2D power spectrum. M33, the whole galaxy has had its Fourier transform. It's the same as the LMC. Uniform power law power spectrum. No isolated clouds, nothing is giant, just a uniform distribution. CO clouds are the CO bright cores of larger atomic and molecular H2 clouds, defined by chemistry and shielding, not structure. The molecular clouds are larger than, that is the H2 larger than the CO parts, and H1 larger still. And they're even larger atomic structures. This is seen in M31 as well. Might be gravitating. We studied the ones in the Milky Way a long time ago and determined that they were virialized. So this is structure from large scales defined by spiral arms probably, with phase transitions all the way down to star formation. Now, sticking on this topic of interstellar clouds, you know of the Larson laws. This is the size line width relation from a recent survey This is using the Dame catalog of clouds, but compiled in this paper. Size versus line width, about a square root dependence. And this was discovered by Larsen, as I said, in 1981. But if we look at other parts of our galaxy, the inner part, this is the galactic center, they lie way up here. And the outer part, this is the far side outer molecular clouds at radii greater than the sun, they lie down here. So it's not a universal size line width relation. It depends on where you are. This is probably a pressure effect. For a given size, if the pressure is higher, your velocity dispersion is higher. And there's a pressure gradient in the galaxy. So what's the reason for this size line width relation? Is it turbulence or is it gravity? So let's look at turbulence for a second. Argument in Kritzuk and then a simulation on the next page, but we start with just the logical argument. You expect the density to scale inversely with size, and if it's a uniform mass, that would be just -3, kappa would be 1. But in general, it's a fractal type distribution, not uniform. But at the same time, for a compressible gas, you expect the volume energy, the energy density is rho sigma squared, and the time scale is the length over the velocity dispersion. Sigma is the velocity dispersion, rho is the density. So the energy density divided by time, it's a ergs per cubic centimeter per second, an energy cascade scale, is roughly constant. That's true for a compressible gas. If it's incompressible, the Kolmogorov spectrum, that density is constant, and then you get the Kolmogorov law where the velocity dispersion goes as the cube root of size. Well, combining these two, we can get these relations. In particular, mass goes as scale to the 3 minus kappa. Now then we look at something completely different. We look at just turbulence, like a stirring of paint in a bucket, or an atmospheric turbulence, atmospheric clouds. And the fractal dimension of the interface between two layers of a turbulent fluid is 2 plus the gradient of the velocity, which brings in that kappa again. And if we say that the fractal dimension from the structure in the mass-size relation is the same as what you get from the stirring, we can solve for kappa, and that gives kappa of about 1/6, and therefore the velocity dispersion going as the square root of size. So that's very fundamental. It's different than the Kolmogorov, which would be 1/3 size, primarily because there's a density here. The density is connected to size also, and we have two relations that connect those. And this was shown by this turbulence simulation. So now here's wave number, and here's energy, log of energy. This is normalized, which tends to flatten it. The inertial range is really tiny here. It's just a factor of 3. This bump here is kind of crowding. The energy can't get to the smallest scales fast enough. It's kind of a bottleneck. This increase here is the boundary condition. So there's just a tiny inertial range. And that's a 1024 cube simulation. To see an inertial range, you really need a big scale turbulence. This is the velocity power spectrum. And so the density scales as the ratio of the kinetic energy power spectrum to the velocity power spectrum. Both have the square of the velocity, and what's left is the density. We know how these scale with wave number. You end up with this. K is the inverse of wavelength. So that's defined to be that -3 kappa from the previous page. Kappa is 0.14. We get the same relation. So a turbulence simulation confirms that simple calculation I just did, that the line width should go about as the square root of size for compressible turbulence. But what about gravity? If we just start with the virial theorem, twice the kinetic, 1 times the potential is the boundary condition, pressure times radius cubed. I rewrite that here. I solve for the velocity dispersion squared here. Now, if we're just looking at a certain sample where we always happen to see the same column density, it's some brightness limited sample, and if we're just looking in the solar neighborhood where everything has about the same pressure, sigma, which is column density, pressure the same, the parentheses is the same, you get sigma squared goes as r, independent of anything. It's just a selection effect. It's neither gravity nor turbulence. It's just a selection effect. So there's this third option. But let's keep going. If these vary, if the column, and that's essentially where Larsen was. All of his clouds had about the same column density. They're all local, so they all had about the same pressure. But now let's look at a bigger sample, and the column density varies a bit. You look at different radii in the galaxy, the pressure varies a bit. We can write it this way. And when gravity is dominant, this term is small. That means column density exceeds the pressure. And then we get the velocity dispersion just goes as the square root of size times column density, with an additional term that's small. And this is Hayer's law. Now plotting column density of this clouds, again from all the thousands of molecular clouds in the galaxy, times radius, column density times radius, velocity dispersion about the square root. So now you would think, well, gravity is important, because it's got that column density in here, which is a measure of gravity. If boundary pressure is important, you have to add that other term, and that ratio here is just essentially the boundary pressure over the self-gravitational pressure of a gravitating object. When you add that, there's another track. Here's the pure gravity, here's the pressure boundary condition, and here's the distribution of clouds. These are the outer Milky Way clouds, pressure dominated. Center of the galaxy, other types of galaxies, local galaxies, large Mazarine clouds, and so on. So you have both. So some clouds are pressure bound, some clouds are bound by gravity. So what causes a science line-width relation? It's a mixture. Sometimes it's a virial theorem, sometimes it's turbulence, sometimes it's a selection effect. So the simplest view, here's what you tell your mother when you go home, of the interstellar medium and star formation. They're stirring everywhere from explosions and stellar dynamics. Produces a generally turbulent ISM, forming a hierarchical density structure, which can be viewed differently with every tracer you happen to look at. Dust, or CO, or H1, dense HCN. That produces correlations, like the size line width, with the magnitude of the correlation depending on pressure. And then gravity takes over here and there, wherever the column density gets large compared to the square root of P over G. When gravity takes over, the turbulent motions convert to turbulent collapse type motions and eventually collapse. So it's stirring, turbulence, correlations, in certain places gravity. So let's look at triggering. The granddaddy of triggering, grandmother of triggering, is spiral density wave triggering. When Lin Shu made their theory of spiral density waves, they had very low potential, 5% potential perturbations. And then when Roberts, their student, came along, he said, well, the reason you see spiral arms is that it's all triggering, triggered star formation. Potential you can hardly see. So it has to be shock fronts, there has to be triggering, and that's why they glow blue. Well, lots of problems with that, because you expect the gas to be compressed more than the star, so you expect the star formation to follow the gas, regardless of, even with a very low potential, that's not necessarily triggering. If star formation is just following the gas, that's not really triggering. Nothing new is happening, it's just all piled up in the arms, which is true anyway. And people have looked for a long time. Sometime they find clouds are more gravitating in the arms. There's one study like that. Other times they don't find that. They rarely find age gradients. And this is the problem. When you look at a galaxy, you could sort of imagine if you're Bill Roberts, you would say, aha, here's my shock front, which he first formulated, this dust lane. And then look at downstream, you see all these bright OB associations. So there's your age sequence. Imagine, it's kind of like the canals on Mars. You imagine that there's something young here, that's the shock front. Then you imagine that time later, as it flows through, you get the star formation. But you're not really seeing it. In fact, the flow in a spiral arm is more parallel to the arm. It comes in and goes along like this. The mass concentration, arm-interarm, is a time concentration. It spends as much time in the arm in proportional to the mass. It's the continuity equation. So really, it's coming in here, it's flowing along the arm for a long time, and it comes out again. It comes to high density flows along the arm and comes out again like that. That's the epicyclic motion of stars, which are all locked together in this similar phases. That's what a spiral density wave is. And then the gas follows from that. So we've always been interested, what is actually happening in these spiral arms? And just recently, Debbie and I and Yuri Evermov looked again at the Spitzer images, and I think you can see this fairly well. Is there a light here I can? Oh. Okay, so look here. This is the Spitzer near infrared. And look at the arms. You can see these little dots. See these dots? Everywhere. These are intensity concentrations in the arm. Everywhere you see these. And this is an image that's like an unsharp mask. I just take the 8 micron, divide by 24, and look at all these dots. Everywhere, everywhere. So these are what you saw with Taurus. They're filaments of snakes that just ate the mice. Filaments that have condensations in them. Everywhere you look, even in the shells. If we compare the Spitzer images to the optical, well, sometimes you see the 3 in a row, like here. We can see it. But right next to it, you can't really see anything here. Sometimes you see it here, barely, but here at 4. Where is that optically? Optically, the problem is there's extinction. The H2 regions are irregular. Often they're to the side of a cloud, just expanding away from the cloud. OB associations are irregular. The actual process is very hard to see. Even when it's so regular and bright in this southern arm near the center, the dust breaks that up and your eye just doesn't see the regularity. So there's something there that's very regular. It's just not possible to see. What we did was study all these clumps, and I'll just show you this one. Ratio of the separation to the diameter peaks at around 3. That's characteristic of instability in a filament. So these are just gravitational collapses locally on that scale. It's about 400 parsec separation. And we see these little lumps in all the Spitzer archive images that have spiral arms. Just shown you once here. So other kinds of triggering, supergiant shells. This is, again, another galactic scale process. You have big open regions because with hardly any shear, these bubbles grow for a very long time. And they just move the gas around, and the next generation of stars is where that gas is, which happens to be between the shells. That's the only place the gas is. Here's another region. So is this triggering, or is this just following the gas? It's certainly following the gas. Is there an enhanced star formation right there? It's hard to tell. In our galaxy, we see the same thing. W5 region in the Perseus arm, 20 parsec scale or so. And it's compressed gas between them, made dense regions as these giant bubbles have expanded. And de Harvang's model is that you started with some kind of maybe a spiral arm shock or some kind of filament. It formed condensations, they blew up, made a next generation in between them. You actually see that in the distribution of stellar ages. Here's the molecular clouds. Here's W5, W4, W3 over here. And here are the clouds now in between the shells. The red is the young regions, the yellow are the old stars. And you can tend to see a concentration of the young regions around the edge and the old regions in the center. Similarly, on small scales, there are many examples of this. Here's a million-year-old core with a 1/10 of a million-year-old region of young stars around the edge. Here's another one. 1 million years, 1/10 of a million years. Here's another, where you see all the young stars around the edge. This is a compilation of 1,300 Herschel images of the galaxy, Milky Way galaxy bubbles, all stacked and with a normalization to the same size. And if we look at the transition from the youngest to the oldest, starless cores, these are protostars. They're all around the edge. But as we go to class 1 and eventually class 2 older, in red sources, they're in the center. So systematically, every single bubble that they found in Herschel, that's 1,300 stacked, shows this tendency for older things in the center and younger things along the edge. All triggered. You know about pillars. I can go back to this region. There's some beautiful pillars here. The pillars show stars right in the head, and there's always a question, were these dense regions that just happen to be swept back by pressures and you're exposing them now, therefore the stars formed independently of that pressure, or were they actually triggered to form stars as a result of the pressure? And we don't know exactly, but we can look at the distributions, and in some cases all the young ones are right there. You haven't been cooking for a very long time, and nowhere else are the young ones. Here there's kind of a mixture, so that could have been a core which is forming continuously. Here's another one, mostly young regions. So it could be that there's, in some cases, an enhancement because of a new compression in that head of the comet, and in other cases it could have been there all along, with stars forming all along and just been exposed with maybe a little bit new compression. These pillars are important because the sun probably formed in a pillar. Here's the Carina Nebula, the two bright clusters and lots of little pillars everywhere. And here's an X-ray image to the same scale. See those two clusters right in the middle? Okay, X-ray everywhere because there have been supernovae. This is an OB association. Typically, these associations have many supernovae. Here it is on a larger scale, supernova all over here, filling in the X-ray. Why is that important? Because a supernova comes from massive stars, and massive stars have not only a CNO cycle, but they have a magnesium-aluminum cycle for fusion. We take 4 hydrogens into a helium because of the catalysis of aluminum-magnesium going around like this. Well, part of that, this leg of it, makes aluminum-26, which is radioactive with a 0.7 million year lifetime. It decays to magnesium-26 excited state, which then relaxes, giving off a gamma ray at 1.8 MeV. And we can map that gamma ray around the galaxy, and here's Carina. The same X-ray supernova remnant stuff. It's just filled with aluminum-26 decaying into magnesium-26, which then relaxes and gives off the gamma ray. In many other regions as well. Cygnus is looking along a spiral arm. Vela is an old supernova remnant. Well, why this is interesting, of course, is in the chondrules of the meteorites. Because these chondrules have aluminum-type inclusions, which contain aluminum-27, but there's a lot of magnesium-26 in these aluminum minerals. And so that magnesium-26, which shouldn't be in aluminum minerals, is there because it used to be aluminum-26. And you can see that just by plotting the distribution of excess magnesium-26 compared to aluminum-27. So that magnesium-26 came from an aluminum form, which was aluminum-26. And what's so important about that is the half-life, 0.7 million years. So somehow you had to go from supernova debris, mixing, solar system formation, disk formation, meteorite or chondrule formation. The youngest things are about a centimeter, millimeter in size. To lock in that aluminum-26, it's also a heat source, as you know. And then over time, those chondrules just stayed and aluminum-26 decayed into magnesium. So that's a pretty quick time scale. And strongly suggests the sun was not only in an environment of supernova, it means it formed in an OB association, not a torus region, but it also formed fairly quickly and probably was triggered. So now I'm going to move on to going back to galaxy scales, the Kennicott-Schmidt law. So Kennicott, starting in 89 and 98, and others before him, plotted star formation rate density versus gas density, power law 1.4. That means at high gas density, the gas is getting consumed faster because it's not just linear. You'd expect linear at zero order because where there's more gas, there's more star formation. And it's a question of whether truly is linear or a little bit different. And he always preferred the steeper law, meaning at high density it's consumed faster, the timescales are faster. 2008, Bigel did a study, and Leroy in a large group of paper with the Things galaxies, finding a slope of 1 on average. Now maybe it still goes up a little bit steeper, but they concluded it was about 1. And they saw for the first time this drop-off below log column density 1, that's 10, and you can see a Kennicott stop there. He couldn't have seen that. So there are two regimes, a steep slope, and these are the outer disks. The color is radius, 0.75 to 1, R25 is all down here. So the outer parts of galaxies are steeper. And putting in the composite, this is just the Kennicott inner disks, recovering that 1.4, main disks, slope 1, outer parts, slope 2. So why all this structure? There have been various theories. This is also the place where hydrogen tends to start to self-shield and make molecules. So a series of papers by Mark Krumholtz, which could fit this part pretty well as just a transition from molecules here and H1 here. And so you got the idea that maybe the molecular fraction was important. Those don't actually work. This part extends as a similar power law, and if you just have molecule formation, it's a much steeper going to zero more quickly. Over a limited range, it looks all right, but doesn't work in detail. So why are there is there this structure? First of all, for some reason, yet unknown, if we look at the full width half maximum of the disk, that is the scale height of the galaxy, it's somewhat constant out to the sun, and then there's a flare, outer parts of galaxy. Now we've known for a long time the Milky Way has a flare in the outer disk, other galaxies too, in the gas. That's because the velocity dispersion approaches a rather constant value, close to the H1 thermal temperature of warm phase. But the column density keeps going down exponentially, so it gets thicker and thicker. But it's somewhat constant here. So in this constant scale height, there's a direct dependence of the density on the column density, because the thickness is here, the same. Here, the density goes down faster than the column density, because it's getting thick. So here you expect the Kennicott relation to be steeper, because the time scale is getting longer faster than just square root of column density. So I think there are three regimes, just what you've seen. Power 2 for gas-dominated self-gravitating regions, where the thickness depends on your column density. That's outer disks, dwarf irregulars, which are all like that, but also GMCs. If you look inside the GMC, you see that same power 2, and I'll show you that. Power 1.5 in main disks, where for some reason, and there's a lot of detailed modeling required to explain this, the thickness is about constant, and then column density is proportional to density. And that's their standard law. Power 1 is entirely a selection effect in this interpretation. Because if you look at a certain molecule, you just see where that molecule is. And there's always a threshold to see that molecule. It's at a certain density. So you're just looking at gas at about that density, or a factor of a couple higher for the internal structure of the cloud. So you always have the same time scale. So the star formation rate just depends on how much of that stuff there is at that fixed density. So that's true for sparse tracers, whatever is a sparse, like CO and normal disks or HCN. Okay, power 2. The general law for just gravity is you've got a column density and a time scale, and that gives you the star formation rate, and then there's an efficiency. But for gas-dominated regions, the mid-plane density just is inverse with the thickness, column density over thickness, and the thickness depends on the column density. So this is the flare. For nearly constant velocity dispersion in the outer parts, as the column density goes down, thickness gets larger. You plug that in, you get your square divided by this rather fixed column density, and for a universal efficiency of about 1%, which seems to be true everywhere, Krumholtz has a recent end review that he's writing, which shows that pretty well. Efficiency, this is another piece of magic. Not only is the thickness about constant in main disks, but the efficiency is about the same. And that just is the red line here plotted on top of 20 dwarf irregulars and a bunch of outer disks. Here are GMCs, also have a slope of 2. Gutenmuth was the first to find this. This is the Kennicott slope. He said, wow, it's steeper than Kennicott-Schmidt. This is inside GMCs, looking at individual protostars and the column that's associated with it. Lada, all of these others, Evans, Gould Belt, and so on. Why is it the same? Now you start with the same thing again. Inside a GMC, it's a density and a free fall time. But you use the Virial theorem to convert all that to line of sight quantities. And you get a squared column density over the velocity dispersion. Now I can look at surveys, plug in the column density and the dispersion point by point. I can get the coefficients and compare to these constants. And I get an efficiency that's about 10%, a little larger than on the galactic scale, because you're zeroing in on stars. So GMCs look the same as outer disks of galaxies. Look the same as dwarf irregulars, because these are gravitating disks, and in the outer disk, gas dominates stars, and dwarf irregulars, gas dominates stars. The gas thickness depends mostly on its own gravity. In main disks, start with the same dynamical model, the same efficiency, but now the scale height's about constant, so you end up with a 3/2 power, which converts to this numerically, which converts to that line, which fits right on top of the Kennicott and Evans plot for a bunch of galaxies, assuming about 100 parsec thickness. There's so much physics hidden here, but magically it doesn't matter for these crude relationships. The Kennicott-Schmidt law is a very crude relationships, because the thickness is about constant in the main disk with a flare in the outer part. The efficiency is about constant. There's always a cool neutral medium, probably because of some feedback effects. And all this works out really nice. If you want to derive this from first principles, You got to spend a lot of money on a big computer simulation to get all these things to work out nice. But I think if you just want to understand roughly why the Kennicott-Schmidt law works, it's because these things happen to be constant, and then you're just looking at gravity. Here it is again. This is from a paper by Xi, who likes to talk about an extended Schmidt law, but let's look at this again. Large conflation of all kinds of galaxies, local U-lurgs and everything else, generally 1.5, but he says, aha, look here. This is in the outer parts of dwarf irregulars and it falls short. I already showed you that it comes down there. But he's using this to say, really, I should have a correction factor, and it shouldn't be 3/2 gas. It should be 1 power gas with 1/2 stars. If you substitute 1/2 of that gas power with stars, you can pull that over. So he says there's a universal law, which is sigma stars to the 1/2 sigma gas. But I really don't think so. I think you expect this to be steeper out here because you have the flare. So I don't think you need this extended Schmidt law. I don't think you want a single law. I think you want 2 laws. At the same time, you have this linear relation, which is often plotted like this. And you have to be careful. This is a big versus big plot, right? You have little galaxies here and big galaxies here. But the linear people like to do that because HCN, for example, obeys the same law in U-lurgs as it does in local molecular clouds. And the linear law occurs for carbon monoxide at low column density, HCN or other very dense tracers, even at high column density and starbursts. Here's an example of CO and M51, the linear law. But this is a main disk going up to about 100 molecules per solar mass per cubic parsec. There's still a tracer. This is a subdominant species. It's still mostly, a lot of this is diffuse gas, diffuse molecular gas, not gravitating. Here's a study of starbursts where CO has a high slope, but HCN has a low slope. So HCN now is a sparse tracer. It's just telling you what the density is there where you happen to be looking. And this now is telling you all the column because it's measuring the total thickness. So why is it the power 1? You can think of this in 2 ways, and I've exceeded my time. I should really quit. It's essentially what I've just said. You're selecting a certain density, and then the time scale is automatically the time scale of that transition density. And so you're essentially just counting clouds. There's a detail having to do with thinking that stars only form in dense gas, but that's just a result of algebra where CO is on a steeper law than HCN. So the ratio, star formation rate per unit molecules goes direct in the same way as the dense gas fraction per unit molecule. And so you get the impression that the star formation efficiency rate per unit molecule is going directly with the dense gas fraction, but that's not the same as saying timescales go away. So here's a schematic, and then finally I'll show the conclusions. Schematic is, if we look at total gas, slope 1.5 in main disk, going to 2 in the flare. If we look at molecules, it's always a slope of unity, because it's just following the tracer until the molecules dominate the gas, and then it goes to the same as the total gas relationship. And the difference between those is the molecular fraction on this log scale. So I'll leave you with the summary. My time is way over, but then I've had some questions already. You've seen about cosmic star formation. You've seen about ISM structure and turbulence and about molecules. You've seen the age sequences and the laws of star formation, which I think are mostly a result of gravity operating in a turbulent medium with the various selection effects from the tracers you happen to be looking at. Okay, thanks.